All right, so here's lesson 2.3 on estimating derivatives, and this is a calculator-based activity is what this lesson is. So you want to make sure you have your TI-84 handy. I have the online TI-84 to kind of help me out with what we're doing here. And again, we get to use the calculator periodically to do stuff, and I don't like using it all the time just because it creates bad habits. But there are times when we need to use it when it's hard to estimate certain things. So as we look at here on problem number one, it says we're going to estimate the derivative of f of x, and f of x is equal to sine square root of x. And we want to find f prime of 2. So we want to find out, okay, what is that instantaneous rate of change at 2 when x is equal to 2? What is that? And again, we will learn how to take it by the derivative of sine square root x later on in this chapter. It requires several different processes. But we're going to just quickly find this numerical calculation. So on the calculator, what we're going to do is we're going to press math. And we're going to go down to option number 8 where it says end deriv. And so when we go down to option number 8, and as we look at it, and this is what I want you to practice for writing as we show our work here. I want you to practice writing the code here. So d dx. So we're going to take the derivative of our function with respect to x. Inside the parenthesis has to be the entire function you're dealing with. So with that in mind, we're gonna have sine square root of x. And then so as I type in the calculator x, and then I'm doing sine secant x squared square root of x. I do need to close that square root. So I do need to go ahead and close the parenthesis after the square root there to let the calculator know, hey, this is the entire function I want you to take the derivative of. And then the last thing we're going to do is we're going to arrow over here, and we're going to tell it to evaluate it for when x is equal to 2. And again, we'll do this by hand later on with some easier problems in another section. But with some of these kind of nonlinear functions, sine function here, it makes it go a little bit quicker. So when I hit enter, and we have that our answer is approximately 0.055. All right, let's try the second one. Second one here, we're going to go ahead and say math option 8. I'm going to take the derivative of, with respect to x, of the following function, ln, and then we got a fraction, so alpha y equals, and then 1 over 5 minus x. Get outside of that fraction, and then I can go ahead and close that, the ln function, and then arrow out, and then I'm going to go say, okay, I want to do it for of 1.3. So as I write my code here, d dx of the ln of 1 over 5 minus x, and x is equal to 1.3. So what is that approximately? And 1.3, hit enter. It's approximately 0.270. Again, these things, as we look at it later on in the chapter, it's a good 2 to 3 minute process to do stuff by hand, especially when we first get started. We got to learn several types of processes with doing mainly not only the derivative of natural log or derivative of sine function, but we also got what's known as the chain rule that we have to do in those problems as well. So next one here says write an equation of the line. So remember, equation of the tangent line tells me that I want to use that y minus y1 equals m times x minus x1. Want to use that formula. We want to find the equation of the tangent line to that curve at x is equal to 1. Fantastic. Well, we need two things here. We do need a ordered pair. Well, we know it's 1 comma something. So let's real quickly figure out what the y value is. So when, what is y of 1? Well, the square root of 1 over 1 cubed plus 1. That is going to be the square root of 1 over 2. And so now we have the square root of 1/2, which if square root of 1/2, if we go through it slowly, would be 1 over root 2, which is also root 2 over 2 if I go through some rationalizing. So that's my second one. I'm not going to go decimal yet. I'm going to leave it like that. We can go decimal, but I mean now I can approximate. Well, square root of one, square root of 2 is 1.414. Half of that would be like 0.707, is what I would have for the y value. Now we need to figure out our slope, so that's where we get to use the math 8 function. So math option 8, and I'm going to take the derivative with respect to x of second square root, and it's a fraction, so alpha y equals, and I have x on top. On the bottom, I want x raised to the third power, and then plus 1. Arrow outside of that. That looks pretty good. I'm going to go ahead and close the function itself. And I want to do it at 1. All right, so for the slope piece, for our slope, we're doing the d dx of the square root of x over x cubed plus 1, evaluated at x equals 1. And that is approximately negative 1.77. Sorry, I looked off to the side. It is negative 0.177. So as I write the equation, we have y minus root 2 over 2 equals negative 0.177 parentheses x minus 1. And again, there's my point slope form. I can go ahead and bring over the root 2 over 2 and say y is equal to root 2 over 2 minus 0.177 parenthesis x minus 1. And that's as far as I have to simplify. And again, if you want 0.070 or 0.707 down there for the root 2 over 2, you can do that if you want. I just went with that to make it a little bit easier on me. The function must be differential to estimate a derivative. That's when we're looking at derivatives from a table. This means that the graph has to be continuous and smooth. And we learn about, in the next section on our lesson on how, what makes a function differentiable. So we'll learn some criteria there. They're saying use the table, estimate what f prime of 3 would be, and then show your answer to at least your work. Well, we know that roughly the average rate of change would be what the f prime of 3 would be. So f prime of 3 is going to be approximately what f of 4 minus f of 2 is over 4 minus 2. So that would be 10 minus 3 over 4 minus 2, which would be 7 halves. So our slope would be roughly 3.5, and they have units here, miles per hour. So always going to make sure we put units on ones when they have context in a table, because usually when we look at it, it's like a point off if you don't put units on there. On the next one, same thing, estimate what w prime of 100 is, and show your work that leads to it. So w prime of 100 is equal to, let's see, where's 100 would be in there. So let's go back and use the same notation. W of 100 minus, W of 120. So 120 minus W of 80 over 120 minus 80. So now grabbing the numbers there, 500 minus 700 over 120 minus 80. That becomes a negative 200 over 40, which is a negative 5. Now, the units here are really, we got to be careful here. Notice the y value, or the W of x function, is actually gallons per second. It's already a rate. So as we write our units, it's gallons per second. And then we get to put another per second. Because again, it was already gallons per second, and when we divide it by seconds again, it'd be per second per second. The other way you can write that is -5 gallons, and then we can say per seconds squared if we want. So -5 gallons per second squared. So those are options for writing your the units on that problem when we notice that the y value in this sense happens to be a rate of change. We can, when we go to find the rate of change of a rate of change, we end up being, we have a kind of crazy looking units there. All right.